In this video, I'm going to show you some more examples of first-order linear differential equations. Before we start, let me remind you that the first-order differential equation in the standard form is in the form of y prime plus p of x times y equals q of x. And for solving this equation, the first step is to find the integrating factor. Usually, we show the integrating factor with mu of x, and it equals to e to the power of integral of p of x dx, which here p of x is the coefficient of y in the equation. After we find the integrating factor, the solution of the equation is 1 over the integrating factor, which is mu of x. So y equals 1 over mu of x times by integral of mu of x times by q of x dx plus c. And don't forget, when you are computing the integrating factor, here in this integral, do not include the constant c. So let us start with our first example. Our first equation is x y prime minus y equals to x squared cosine of x. Note that this equation is not in the standard form, because the coefficient of y prime in the standard form is 1. But here the coefficient of y prime is x. So the first step before we start and find the solution is to convert this to the standard form. To do so, we have to divide both sides of this equation by x to get rid of this x. If we divide xy prime by x, we have y prime minus, if we divide y by x, we have 1 over x times y, or y over x, equals to, if we divide x squared cosine of x by x, we have x cosine of x. Now our equation is in the standard form. The first step for solving a linear first order differential equation is to find the integrating factor. First, we have to find mu of x. Mu of x equals to e to the power of integral of p of x. Note that in this equation, p of x is negative 1 over x, and q of x is x cosine of x. So we have e to the power of integral of p of x, and p of x is negative 1 over x dx. We know that integral of 1 over x dx is ln of x. So integral of negative 1 over x dx is e to the negative ln of x. So this is the integrating factor for this differential equation. But note that you can simplify this integrating factor with this property. E to the power of ln of x, or e to the ln of any expression like f of x, not only x, any expression, equals to the same expression. But here, because here we have a negative, first we have to get rid of this negative here, then we can use this property to simplify this expression. We can move this negative to the power of x. Logarithmic functions have this property that we can bring the power to the front, or we can bring the coefficient to the power of the expression. So we can write e to the negative ln of x as e to the power of ln of x to the negative 1. And now if we use this property, e to ln of any expression equals to the same expression. So this equals x to the negative 1. So the integrating factor is x to the negative 1. Now we can use this formula for finding y. Y equals to 1 over mu of x, or integrating factor, which is x to the negative 1. So 1 over x to the negative 1 times by integral of mu of x, which is x to the negative 1, times by q of x. Note that you have to use this as q of x, not this function in the original equation, because the original equation is not in the standard form. We have to use this as our equation in this formula. So q of x is x cosine of x dx plus c. Note that x times x to the negative 1 is 1, because the power of x is 1 here, and x to the negative 1 is 1 over x, and so these two cancel each other. So we have to integrate only cosine of x, because these two multiply by each other and they equal 1. Integral of cosine of x is sine of x, and 1 over x to the negative 1 is x, because if we bring x to the negative 1 to the top, if we make the power positive, it equals x. So we have x times by integral of cosine of x is sine of x plus c. This is the general solution for this given differential equation. Note that here we cannot find this unknown constant c, because we don't have any initial condition for this given differential equation. In this example, we want to solve this equation: sine of x times y prime plus cosine of x times y equals 2. And in this equation, we have this initial condition: y at pi over 2 equals 0. So we have an initial condition for this differential equation. And so we can find the particular solution for this differential equation. First of all, note that this first order linear differential equation is not in the standard form, because coefficient of y prime is not 1. So first we have to divide both sides of this equation by sine of x to get rid of sine of x and make the coefficient of y prime equal 1. If we divide every term of this differential equation by sine of x, we get to this equation. In this term, sine of x from the top and sine of x from the bottom cancel each other, so we get y prime plus cosine of x over sine of x is cotangent of x. We know from the trigonometry that cosine of x over sine of x is cotangent of x. So you can write this as cotangent of x, or you can leave it in this form. It's up to you. Here I prefer to leave it as cosine of x over sine of x times y equal to 2 over sine of x. Now our differential equation is in the standard form, because the coefficient of y prime is 1, and so this is a first order linear differential equation. The first step is to find the integrating factor. Note that in this equation p of x, coefficient of y is cosine of x over sine of x, and q of x is 2 over sine of x. So the integrating factor mu of x equals to e to the power of integral of p of x, which is cosine of x over sine of x dx. Integral of cosine of x over sine of x is ln of sine of x, or actually ln of absolute of sine of x, which here I am writing only sine of x. If you don't know why integral of cosine of x over sine of x dx is ln of sine of x, let me show you why this integral is ln of sine of x. For finding integral of cosine of x over sine of x dx, you can do a simple u substitution. If you choose the denominator of this expression to be u, du is cosine of x dx, and so we can write this integral as du over u. All the expression in the top is du, as you can see here, and the expression in denominator is u. And we know that integral of du over u, or 1 over u, is ln of u. But u is sine of x, so the integral of this expression is ln of sine of x. Let's back to our question. But we know that e to ln of any expression equals to the same expression. So e to the power of ln of sine of x equals to sine of x. So sine of x is the integrating factor. Now we can find the solution of this differential equation. Y equals to 1 over integrating factor, which is sine of x, 1 over sine of x, times by integral of mu of x sine of x times by q of x, which q of x is 2 over sine of x, times by 2 over sine of x dx plus c. Note that sine of x from the top and the bottom cancel each other, and so we have only 2 here. And integral of 2 dx is 2x, so this equals to 1 over sine of x times 2x plus c. So this is the general solution of this differential equation. But here we are asked to find the particular solution because we have an initial condition for this differential equation. So we can use this initial condition for finding c. If we plug in pi over 2 for x here and here, the y value, the y equals 0. So we have to plug in 0 for y, and we have to plug in pi over 2 for x. So if we use this given condition, we have 1 over sine of pi over 2 times y. 2 times x, 2 times pi over 2 plus c, this should equal to 0. Note that we have to plug in 0 for y, so this should equal to 0. Sine of pi over 2 is 1, so this fraction is 1, and we have to set this bracket actually only equal to 0. So we have pi plus c equals 0. Note that 2 times pi over 2 is pi. And from here, c equals to negative pi. Now if we plug in negative pi for c here, we can write the particular solution of this differential equation as y equals to 1 over sine of x times by 2x minus pi. We have to replace negative pi for c. And this is the particular solution of this equation. In the next question, we are given this differential equation dy over dt plus 2y equal to 5, and we are asked to find y of t, and also we have to find limit of y of t as t approaches infinity. So first we have to solve this differential equation, and then in the next step we have to find limit of the solution as t goes to infinity. First of all, note that in this differential equation, instead of variable x as the independent variable, we have variable t. And so this is the reason instead of y of x, we have y of t here. And also note that this differential equation is in the standard form because the coefficient of y prime, dy over dt, is the same as y prime. But note that the y prime is with respect to t. The variable here is t, not x. Coefficient of y prime is 1, so the differential equation is in the standard form. The first step for solving this differential equation is to find the integrating factor. Integrating factor, which usually we show it with mu, note that here it's not mu of x. In this question it's mu of t, because instead of variable x we have variable t. So mu of t is equal to e to the power of integral of p. Note that here in this equation p is constant 2. Very simple function 2, but note that do not put dx, dt, because again the variable, the independent variable in this differential equation instead of x is t. So integral of 2 dt is 2t. So e to the power of 2t is the integrating factor. Now we can find y, or actually y of t. The reason that here we are writing this t in the bracket is to emphasize that the variable instead of x is t. If you do not like to write it this way, you can simply write y. It's up to you. So y, or y of t, finally is 1 over integrating factor, which is e to the power of 2t, times by integral of integrating factor mu, which is e to the power of 2t, times by q, which is 5, times by 5 dt plus c. Note that 5 here is a constant. You can put it behind the integral. And integral of e to the power of 2t is e to the power of 2t over 2. Let me remind you this formula from the integral. Integral of e to the power of at dt, which a is a number here, equals to 1 over a e to the power of 80. So integral of e to the power of 2t is 1 over 2 e to the power of 2t plus c. If we multiply this 1 over e to the 2t in this bracket, when we multiply this in the first term, e to the 2t and e to the 2t cancel each other. So we have 5 over 2 only. 5 over 2 remains, 5 in top, 2 in bottom, plus if we multiply this 1 over e to the 2t times c, we have c over e to the power of 2t. Or if you like, you can write this as 5 over 2 plus c times e to the power of negative 2t. So this is the general solution of this differential equation. Now we can find the limit of this expression as t approaches infinity. Limit of 5/2 plus c e to the power of -2t as t approaches infinity is 5/2. Note that when t goes to infinity, e to the power of -infinity approaches 0. T goes to infinity, so -2t goes to -infinity, and e to the power of -infinity is 0. Let me show you here the graph of the function e to the x. As you can see in this graph, when x goes to -infinity, the y value of this function approaches 0. This distance between the curve and the x-axis gets smaller and smaller. So limit of e to the x as x goes to -infinity is 0. And here also the power goes to -infinity. So the limit of this part is 0. And so the limit is only equal to 5/2. In this example, we want to find the general solution of this differential equation. And also we want to find the limit of the solution as x goes to infinity. So first we want to find y, or y of x actually, and then we want to find the limit of y, or y of x, as x goes to infinity. Note that this given differential equation is not in the standard form of a first order linear differential equation, because coefficient of y prime should be equal to 1, but here the coefficient of y prime is x squared plus 1. So the first step is to divide the left side and the right side of this equation by x squared plus 1. If we divide left side and the right side of this equation by x squared plus 1 to get rid of x squared plus 1, we get to this equation, y prime plus 3x over x squared plus 1, y equals to 6x over x squared plus 1. Now we can start to solve this differential equation, because now the equation is in the standard form. First, as usual, we have to find the integrating factor. Mu of x, the integrating factor, is e to the power of integral of 3x over x squared plus 1 dx. Integral of 3x over x squared plus 1 is 3/2 ln of x squared plus 1. Let me show you how you can find this integral. For finding the integral of 3x over x squared plus 1 dx, simply you can consider the expression in denominator x squared plus 1 as u, and then du is 2x dx. So here we are doing a u substitution, and so from this we get dx is du over 2x. Now if we replace dx with this expression and x squared plus 1 with u, we have integral of 3x over, we are replacing this with u, and we replace dx with du over 2x. Now x from the bottom and the top cancels, so we get to 3/2 is a constant, so we can put it outside of the integral. Integral of du over u. And integral of du over u is ln of u, so it is equal to 3 over 2 ln of u, but u is x squared plus 1, so this integral is equal to 3 over 2 ln of x squared plus 1. This is how you can find this integral. Okay, let's back to our question. So this expression is the integrating factor, but we have to simplify this first. If we move 3 over 2 to the power of the expression here, we can write integrating factor as e to the power of ln of x squared plus 1 to the power of 3 over 2. We know that e to the power of ln of any expression equals to that expression. So this equals to x squared plus 1 to the power of 3 over 2. So this expression is the integrating factor in the simplified form. The answer of this differential equation is 1 over mu of x, or integrating factor, which is x squared plus 1 to the power of 3 over 2, times by integral of mu of x, or integrating factor, which is x squared plus 1 to the power of 3 over 2, times by q of x. Note that this expression is not q of x. This expression 6x over x squared plus 1 is q of x, because this equation is in the standard form, not this equation. So you have to use this for q of x. So times by q of x, which is 6x times over x squared plus 1 dx plus c. We can simplify x squared plus 1 in denominator, which has power 1 here, with x squared plus 1 to the power of 3 over 2. If we cancel and simplify this with this, x squared plus 1 with power 1/2 remains in numerator. So we have y equals to 1 over x squared plus 1 to the power of 3 over 2 times by integral of 6x times by x squared plus 1 to the power of 1/2 dx. Again, if we simplify this part of the expression, x squared plus 1 to the power of 3 over 2 over x squared plus 1 is x squared plus 1 to the power of 1/2. Because if we subtract the power of the top from the power of the bottom, which is 1, 3 over 2 minus 1 is 1/2. Now we have to find this integral. Integral of 6x times by x squared plus 1 to the power of 1/2 is 2 times x squared plus 1 to the power of 3 over 2 plus c. Let me show you why this integral equals to this expression. For finding the integral of 6x times x squared plus 1 to the power of 1/2 dx, you have to do simple u substitution. If we choose x squared plus 1 as u, then du is 2x dx. And so we can write dx as du over 2x. If we divide both sides of this relation by 2x, dx is du over 2x. Now, if we substitute this and this in this integral equals to, this expression is u, so we have u to the power of 1/2 times 6x times dx, which is du over 2x. X from the bottom and x from the top cancels, 2 from the bottom and 6 cancels, a 3 remains here. So we have 3 times u to the 1/2 du. Integral of u to the 1/2 is u to the 3/2 over 3/2. If we cancel 3 with 3 and we move 2 to the top, we have 2u to the 3/2. But note that u is actually x squared plus 1. So this equals to 2 times x squared plus 1 to the power of 3/2. So this integral equals to this expression. This is how you can calculate this integral. So this is the answer of this given differential equation. This is the general solution of this differential equation. Now we have to find limit of this expression as x goes to infinity. For finding limit of y as x goes to infinity, it is better to multiply this expression in the bracket. If we multiply 1 over x squared plus 1 to the power of 3/2 in this bracket, x squared plus 1 to the power of 3/2 cancels with this expression. So y is actually 2 plus c over x squared plus 1 to the 3/2. Again, how we find this y? We multiply this expression in the bracket. When we multiply 1 over x squared plus 1 to the 3/2 in the first term, x squared plus 1 to the power of 3/2 cancels with this and a 2 remains. And when we multiply this in c, we get this expression. Now we have to find limit of this expression as x goes to infinity. Limit of 2 plus c over x squared plus 1 to the power of 3/2 as x goes to infinity equals 2. Because when x goes to infinity, a constant over something that gets larger and larger as x goes to infinity, a number, a constant over infinity is 0. And so the limit equals 2. I hope you enjoyed this video. If you like this video, please subscribe in my channel. See you in the next videos.